Hello, I'm Ben Manning, and this presentation is over the jetting process, which covers chapters 7 and 8 from Additive Manufacturing Technologies. Specifically, I will be discussing material jetting and binder jetting. Now, what makes material and binder jetting similar is through the deposition of a material to create the desired part. Material jetting achieves this through the deposition of a liquid material dispensed in droplets primarily through a printhead, while binder jetting only utilizes a small amount of the material through the printhead, which is usually the binder, onto a powder bed. On the subject of material jetting, it can trace its roots all the way to the 1960s through inkjet printing, which is pretty commonplace even today. Three-dimensionally, this building method was first introduced in the 1980s through the development of ballistic particle manufacturing, where a flow of a material is ejected through a small orifice and placed on a surface using a kind of mechanism much like an inkjet. The first models to print in 3D used a kind of waxy thermoplastic that was heated to a liquid state. However, more recent devices have been more focused on the use of acrylic photopolymers, where upon deposition, droplets of liquid monomer are formed and then exposed to ultraviolet or UV light to promote polymerization, meaning that under this light, monomers will take shape and solidify. Now, in material jetting, polymers are king. Polymers such as the aforementioned photopolymer and other waxes remain the only material in the material jetting process that is commercially available. In large part, this is due to the viscosity of the liquid materials. Commonly, the maximum printable viscosity is around 20 to 40 centipoise, which is an equivalent unit to millipascal seconds. However, high viscosity liquids can negatively affect droplet formation and clog the nozzles. A solution then to lower viscosity would be to simply heat the liquid, but this can negatively affect the machine components if heated too high. Another solution then would be through solution and dispersion based deposition, which utilizes a carrier liquid with the adequate viscosity and contains a solid or high molecular weight polymer. Now, ceramics is such a material that uses this technique. Ceramics, when used, has shown to have some success in printing through the use of such a carrier with moderate viscosity. However, high concentrations of suspended powder can make the viscosity too high to print, and the parts yielded are only partial ceramic density, which can lead to shrinkage. Furthermore, low concentrations of polymer and solid within the solutions and dispersions can restrict the amount of material that can be deposited. Also, it can be challenging to control the deposition pattern on impact of the droplet, but this can be rectified by controlling the droplet drying conditions. Lastly, the main issue with this technique is that the use of more volatile solvents can result in premature formation of precipitation within the nozzle and cause clogging. Though significantly less common, there is some work into the 3D aspect of metals. Copper, aluminum, tin, and mercury are such metals that have been tested in printing to some degree of success. And unlike ceramics, the metals that are being printed using material jetting have a very high density and more uniform microstructure. Now, there are two main classifications within this process which have to do with the droplet expulsion: continuous stream and droplet on demand. In continuous stream mode, a steady pressure is applied to the fluid reservoir, which allows for the column of fluid to be ejected. The stream then forms into droplets through Rayleigh instability and can be controlled through vibration at a fixed frequency. To create constant intervals, the droplet formed are introduced to a charging field and given an electrostatic charge before passing through a deflection field that directs the particles to the desired destination. This results in the formation of droplets of equal mass and equal intervals. For drop on demand, individual droplets are made in the nozzle directly and are formed when independent pressure pulses in the nozzle cause the fluid to be expelled. To create pulses in pressure, various types of actuators are used. The two main actuators used are piezoelectric and thermal, otherwise known as bubble jet. The thermal actuator uses a resistor to heat the liquid until a bubble forms within the reservoir, which forces the droplet out, while piezoelectric actuators rely on the deformation of a piezoelectric element to reduce the volume of the reservoir to force the droplets out. Now, the benefits of material jetting are similar to those others in additive manufacturing processes. It's low cost, high speed, easy to scale, and can easily build parts in multiple materials, with an added benefit of color printing. However, there's a limited number of materials that can be used at the moment, and part accuracy does not compare well with other processes. This is especially true with larger parts. Now, binder jetting prints a binder into a powder bed to create a part, thus only a small amount of part material is printed through the print head. The binder droplets, when printed, form a collection of binder liquid and powder particles and then bonds to the previous layer. When a layer is completed, the powder bed is lowered and another layer of powder is spread and is repeated until the desired part is complete. The completed part is then commonly left on the bed until the binder is fully set and the green part is fully strengthened. The part is then separated from the bed, any excess powder is removed, and the part is infiltrated to make stronger. Now, there are a lot more parts commercially for binder jetting than there are for material jetting. However, these parts are typically weaker. Therefore, they are infiltrated with another material. There are a variety of infiltrants as well, commercially, and can range from a simple acrylic-based infiltrant to a more complicated two-part infiltrant. Now, for the creation of metallic or ceramic parts, the green part must be removed from the machine and then placed in a furnace at least 3 times. The first time at low temperature to burn off the binder, the second time at a higher temperature to sinter the particles together and strengthen it, and the last time to infiltrate it with either a bronze ingot for metals or with another material, including metals, for ceramics to strengthen the part. Furthermore, early use in ceramics saw setbacks that were due to the use of dry powders, which did not flow well. To counteract this, a slurry-based working material was used. Layers are first deposited through the use of an inkjet, printing a layer of slurry over the build area. The slurry then dries, and the binder is selectively printed to create the shape and repeated as necessary. Now, most commercial binder jetting machines follow the same design as shown below. However, there are differences in the plaster and polymer powder machines and the metal and sand machines. The plaster and polymer machines are lower cost, and their containers for the powder are typically small enough to be carried by hand, while the metal and sand machines have containers that could weigh hundreds or thousands of pounds and are more costly. These larger machines have rail systems for moving powder beds to and from depowdering stations, and larger equipment like cranes are used in moving the created parts. Now, another part of binder jetting that has come up is through continuous printing. There has been plenty of discussion on the ability for continuous printing or making parts larger than the additive manufacturing machine. One such approach, commercialized by VoxelJet, utilizes an inclined plane angle of 30 degrees, which is a small enough angle for the powder to not be affected. The recoating and binder jetting are actually done at this angle, and the powder bed moves from front to the back of the machine, which is the opposite from the normal process. The parts produced have the ability to have any length required, infinite if desired, with no limitations from the size of the machine. The second approach utilizes a circular powder bed with constant rotation and continuous binder printing and recoating. While in motion, the powder moves down the spiral continuously to make room for the next layer. Moreover, the top layer creates a spiral in the powder bed. There are also several build stations that each contain a print head with multiple nozzles. A side effect of this design, however, is that the images printed must be pre-skewed to compensate for the differences in speeds of the powder bed. Now, benefits and drawbacks to binder jetting share many of the same benefits as material jetting, with some distinctions. It can be faster since less material is going through the print head. Binder jetting also allows for a combination of powder, materials, and additives not possible or extremely hard to get using direct methods. Slurries with higher solid loadings are possible with binder jetting, allowing for better ceramics and metal parts to be produced. However, the need to distribute powder adds another step, which can slow the process down, and parts made from binder jetting processes also tend to be a little less accurate and have poorer surface finish than material jetting. Now, in conclusion, material jetting and binder jetting share as many differences as they do similarities. While they both require the use of a print head to deposit a material onto a substrate, binder jetting only subjects a small portion of the material to the print head, while material jetting utilizes all of the material. Material jetting also uses liquid, while binder jetting incorporates more of a powder material and a binder. There is a much broader range of materials that can be used for binder jetting, while material jetting can be limiting. However, especially for smaller parts, material jetting is more accurate and has a better finish, while binder jetting is more for larger parts. The binder jetting process is more suited for ceramics and metals, while material jetting is more for polymers. Both processes are relatively low cost, low energy, and commonly non-toxic, with the added benefit of color printing. Therefore, both jetting processes demonstrate that while very similar, they have individual strengths and weaknesses that can be used to create a variety of parts. All figures come from Additive Manufacturing Technologies by Ian Gibson, David Rosen, and Brent Stucker. Thank you very much for your time and have a great day.